Hey everyone, welcome back to another calculus video. We're going to talk about derivatives of trig functions today. And so there are 6 trig functions: sine, cosine, tangent, cotangent, secant, and cosecant. And today we're going to explore where the derivative of sine comes from. Now what I do here with sine is similar to what you would do to derive the derivatives of the other 5 trig functions. I'm not going to take time in this video to do that and to walk you through it, but I'm going to at least let you see the process. Now, this process is not something you'd be required to do on a test or anything like that. You would be required to memorize the results. And truthfully, that's going to be the case for a lot of these derivatives that we're going to be learning over the next few videos here. But I think it's also very important to always revisit that derivative definition so that we can see where those derivatives are coming from. And so let's kind of review what that looks like. Now, the definition of a derivative says that if I think about the limit as h approaches 0 for a function, it would be the limit of sine of x plus h minus the derivative of sine of x. So it's that whole, slope formula, f of x plus h minus f of x over h. So that limit is your definition of the derivative. So let's see if I can show you a little bit better. There it is. So there's my definition of a derivative up there in that upper right corner. So that's what we're applying here to find this derivative of sine. So let's take a look and see what that looks like when we work it out. Now, normally when we evaluate a limit, as we consider h approaching 0, we would try to use substitution. And the problem with this definition of a derivative is anytime we use it, we get what's called the indeterminate form. We get 0 over 0. And it's important to understand that 0 over 0 is the indeterminate form because, remember, we're not plugging 0 in. We're saying as we approach 0, what value do we head towards? And when you get a number like 0 over 0 when you're evaluating a limit, or infinity over infinity, what's happening is the numerator is approaching 0, the denominator is approaching 0. The trouble is they're not necessarily approaching 0 at the same rate. And that's why it's called the indeterminate form. So for example, if you get infinity over infinity, if one function is approaching infinity faster than the other one, then truly the limit will not necessarily be 1, as you might think, infinity over infinity. Oh, that must be 1. Not all infinities are equal. So if the numerator is approaching infinity faster than the denominator, well then it would be reasonable to think that we should get some other sort of value potentially as our result. And similarly, if the denominator approaches that value faster, we would expect a different result. So it's all about how fast are we approaching that 0 or that infinity that's in that indeterminate form. So we're going to learn some other tips and tricks later on for evaluating those indeterminate forms. But for now, just understand when you get 0 over 0, you've got to take some more steps. Now, to evaluate this limit, we're going to have to call upon some trig identities. So I'm going to use this trig identity. It says the sine of a plus b, because we have this x plus h floating around, is sine of a times the cosine of b plus the cosine of a times the sine of b. Now, you may not have that memorized from your pre-calc or your trig class, but just so you know, this is an identity that we're going to have to use, and it exists, and if you Google it, you'll find it. And it looks a little bit like this. When I go to plug it in, I'm still going to consider the limit as h approaches 0. I'm still evaluating a limit, but it'll look like this. X will be my a, and h will be my b. So when we plug everything in, this is what we look like, and using that trig identity. Now, here's how I'm going to simplify this. I'm going to gather some terms that are similar or alike altogether. So I see I have a sine x and a sine x. So I'm going to reorganize my work here and rewrite it like this. The limit as h approaches 0. I'm going to keep that first term first. Put the minus sine x here. There we go. So all I did was kind of rearrange a little bit. And what this is going to allow me to do is, out of these terms, I'm going to go ahead and factor out a sine of x. Because here's the deal. If I have variables in my factors or terms in the little pieces and the little functions within the function, if they don't have an h in it, they're not going to be evaluated. They're just going to be a part of the answer. So what I can do is, if I can find a way to get those out of my problem, factor those out, I can pull them out of the limit, because sine of x is just going to stay sine of x. I'm concerned about sines of h, or cosines of h, because that's the variable that's approaching 0. So the sine of x doesn't get impacted by the behavior of h. So here's what I'll look like. The limit as h approaches 0. I'm going to factor out my sine, and I'll have cosine of h minus 1 plus cosine of x sine of h. That stays put all over h. Now, here's what I'm going to do to continue with this. I have two terms now, and each of these terms, I can evaluate the limits separately. So here's what I mean. I can take this term and put it over h, and then I can take this term and put it over h. And when I do that, it allows me to evaluate each piece separately. Here's what it looks like. There we go. So I've split it up and I've made two fractions. And remember, to put the two fractions together as one, we had to have a common denominator. So it makes sense that if I have one fraction that's been put together, I can take it back apart and put it over that common denominator of h. Now I'm going to be able to factor out this sign. So here's what it looks like. The sine of x times the limit as h approaches 0 of cosine of h minus 1 over h. Now I'm down to all the h's. I've pulled out the x's. And I'm going to do the same thing over here on the right, because x is not impacted by anything that h does. And now check this out, everyone. This we should be really familiar with. We should hopefully know that this goes to 1. That's the limit of this function. We explored that graph in an earlier video. Now our problem, however, lies with this here in yellow. Now, this value we don't know anything about, and we don't have the tools to explore it without a graph. So for now, I'm just going to ask that you trust that the graph, as we look at this limit when h is approaching 0, the graph of this function actually approaches 0. And so what this does for me is now I have 0 times the sine. Well, that's going to make the sine go away. And then I have 1 times the cosine. Well, what I've just done is I have shown that the derivative of sine of x ends up being cosine of x. Now, this is where the derivative comes from, and if we take a look at the graph here on Desmos, we can kind of see, you know, the relationship here, and I can prove it to you using Desmos. So Desmos will take and graph this sine, and then I can actually program it to graph the derivative of a function using that Leibniz ddx notation. Desmos is really pretty cool for that, and if you're working at home, I highly recommend using Desmos for this. It's much faster than your graphing calculator, much more powerful. And you could similarly look at the graphs of cosine and see what the derivative of cosine is. But for the sake of time, I'm going to put a couple of formulas here on the screen. And I recommend copying these formulas down because these we're going to memorize. We're not going to necessarily do the work to see where the derivative of cosine comes from. But if you use the sum formula from the trig identities for cosine of a plus b, and you worked it out similarly to what we just did, you would find that the cosine of x has a derivative that is negative sine. So it's really important to understand that there is a sign change when we find the derivative of cosine. So it's a negative sign. So as you copy this down, great, awesome. Let's see how it's applied, because this video would be pretty boring if all we did was look at sine of x and cosine of x. Let's see some more common applications of where we're going to use these derivatives. In particular, we're going to use them within derivatives of other functions that require the use of the product rule and the quotient rule. And then in the next video, we're going to discuss something called the chain rule. And the chain rule will also be used with our trigonometric functions. But that's another video for another day. So let's talk about this derivative, x squared times sine of x. This is a classic product rule problem. So let's review what that product rule is, if I can spell it correctly. Product rule. There we go. The product rule says that when I have two things that are multiplied, u times v. Well, that's what I have here. This is u, and this will be v. Now, it doesn't matter in multiplication which one's first or second. It's just a matter of which one is listed first. Remember, multiplication is commutative, and within our product rule, we see we're going to have addition. Addition is also commutative. So no matter which one you designate as u or v, you should always get the same result, provided that you're applying the product rule properly. So it's the first times the derivative of the second plus the second times the derivative of the first. So we need to find what u prime is and v prime. So if I let u be x squared, u prime will be 2x, meaning that if v is sine of x, and here's where we're going to use our new derivative, v prime is cosine of x. So when I plug things into my product rule, here's what it looks like. I'm going to have u times v prime, so that's going to be x squared, there's my u, times v prime, that's cosine of x, plus, and then it says v, that's going to be sine of x, times u prime. Well, that's 2x. Now, the only thing that I would say here is once you get everything plugged in, remember to wrap everything with parentheses. We want to make sure that we don't ever mistake that, for example, the 2x here on the end. We don't want to ever think that's part of the angle that we're taking the sine of. It's a whole separate little sub-function within our function. So what I'm going to do is I'm going to take anything that's not part of the angle and I'm going to move it to the front and treat it as a coefficient. So I'll have x squared cosine x plus 2x sine x. And still, there's nothing wrong with keeping everything in parentheses. That's actually a really good habit to get into, because as you're moving quickly and trying to work through things and finding derivatives and so whatnot and so on and so forth, keeping things tightly wrapped up in those parentheses are going to keep you from accidentally misinterpreting your work. Because if your brain is going a mile a minute, whoops, I've seen it happen. You misread what you've written and then you go on and you do the rest of the problem wrong. So parentheses are a good habit to have. So there's my derivative. Let's talk about this one. So this derivative is a quotient, and in order to find the derivative of this function, we're going to need to review our quotient rule. So let's write that down. The quotient rule says this. If I have u divided by v, now remember we like to use the words high and low, so I'll write them here in red. So it says this. It's going to be v times u prime minus u times v prime all over v squared. Now, we like to remember it because we label these low, and so we say it's low times the derivative of the high, low d high, minus high d low. Remember, high d low always comes in last. So she's this runner at this school, and she's always coming in last. And this is a story that we tell with the quotient rule. But Heidi Low always comes in last. She's the worst runner on her cross-country team. She loves to run, but she's always last. Poor Heidi Low. And then again, it's all over low squared. So that's another way to kind of memorize this, because with a quotient rule, just like division, it matters which one's in the numerator and which one's in the denominator. Subtraction is also dependent on which one comes first. So if the most common mistake with the quotient rule is you accidentally switch the two terms. You want to remember Heidi Low is always last. So let's figure things out. Let's write it down. So we got low is 1 minus sine of x. The derivative of the low, okay, now this is where it's tricky. So you have 1 minus sine x. Well, that negative is like a -1, right? So just like when we do our power rule with our polynomials, we want to multiply, we want to keep that constant that's in front. So my derivative is still going to be negative, but this time it'll be negative cosine. Okay, and then my high is cosine. The derivative of the high is negative sine. So let's plug things into our quotient rule and see what it looks like. So here we go. So we're going to go low d high, so we're going to have 1 minus sine x times the derivative of the high, which is negative sine x, minus Heidi Low, cosine of x, times negative cosine of x. And it's all over low squared, 1 minus sine of x squared. Now remember, when you do your quotient rule, you want to always remember that the numerator has to be worked out. You have to simplify that numerator. The denominator, I'm not going to require that. But there are times when this will simplify into something, and you might be able to simplify it further. And on a multiple choice question on the AP exam, being able to simplify is a very critical skill for success. So let's simplify this and see what it looks like. So I'm going to multiply and distribute that negative sign throughout, and I'll have negative sine of x plus sine squared x minus, actually it's going to turn into a plus because I'm going to have minus and minus. So plus cosine squared x, that should look familiar, all over 1 minus sine of x, all being squared. So let's check this out. Sine squared plus cosine squared, we should know what this is. It's a Pythagorean identity. It should be just one. That should be an identity that we know. There's a couple of identities that show up on your AP exam frequently. This is one of them, and it's a nice easy one, and hopefully we all remember it. But here we go. Now we're left with negative sine of x plus 1 all over 1 minus sine of x squared. Now, when I see that I have sine and 1 and 1, here's where I need to pay attention to see what do I need to do. Sometimes I'll need to rearrange the numerator. Another thing that happens often is sometimes you can factor out a negative 1. So if you notice you have the same exact thing in the numerator and the denominator, but the signs are different, try factoring out a negative 1. In this case, we don't have to do that. We just have to rearrange 1 minus sine of x. And lo and behold, remember, I can only cancel things if I can wrap them in parentheses and cancel the entire thing. So I can cancel that with one of the ones on the bottom, and I'll be left with 1 over 1 minus sine of x. This is the derivative that I would be looking for on your test. And this is the type of simplification that I'm asking you to do. On a multiple choice exam, this would be the answer listed. So if you stopped at what we had up there in green, or even what we had down below that very first time in purple, you wouldn't find that answer listed on a multiple choice exam. You'd find this one here that's circled in red. Let's take a look at a couple of the other trig functions. Now, I am going to walk us through finding the derivative of tangent. And so, oops, there we go. And we can see in the bottom, I'm not very good at hiding things. But let's see where the derivative of tangent of x comes from. Now, if I'm going to find the derivative of tangent of x, I need to use some sort of trig identity. And I'm not going to use necessarily the definition of the derivative here because I don't want to have to recall the tangent of alpha plus beta. I think that's annoying. So what I'm going to do is I'm going to use other methods here. I'm going to rewrite the tangent using a different trig identity. Sine of x over cosine of x. And then I'm going to use the quotient formula. So this is high and this is low, right? So high and low. So here we go. Low d high, so cosine of x, that's low. And then the derivative of sine is cosine. Minus high d low, right? Sine of x. The derivative of cosine is negative sine of x. All over low squared. Okay, so I've plugged it in. Now let's simplify. Cosine squared x plus sine squared x, that's familiar. All over cosine squared x. Well, that's just going to be 1 over cosine squared x. Well, maybe you remember what 1 over cosine is. It's just secant. So the derivative of the tangent is secant squared. So here are a few more formulas that you should jot down. And I want to talk about this little thing here on the screen, this gal who's whispering psst, psst. Because as you're copying these down, there's a nice, easy way to remember them. Remember, there's no formula sheet on your AP exam, so you need to memorize these. And so an easy way to remember them is, you know, when you're sitting there without a formula sheet on your exam and you're tempted to phone a friend, which is not okay, what do you do to get their attention, right? On test day, you lean over and you go, psst, psst, hey, do you have the answer? Do you know what the derivative of tangent is? Well, psst is your reminder, and it goes like this. If you can remember that these s's are secants and the t is a tangent, here's how you can remember those derivatives. If you draw arrows pointing inward, it goes like this. The derivative of tangent is secant times secant, secant squared. Similarly, the derivative of secant is secant times tangent. And so this is the formula that we have, and this is how we remember it. And you can even use it to remember the cofunctions. So if you remember the cofunction of secant is cosecant, and the derivative and the cofunction of tangent is cotangent, the one difference is when we do that, we have to put the negative sign in the middle. And if you can remember, oh, the derivative of cotangent is negative cosecant cosecant. Well, that's negative cosecant squared. Similarly, the derivative of cosecant is negative cosecant cotangent. And so this is how we can remember these trig functions. Sine and cosine, that's pretty easy. But these other four, it can be tricky. So just remember, psst, that's your trick, okay? So let's see them in action. Find the second derivative if y is secant of x. So we're going to remember, psst, and true story, I think this in my head all the time when I'm like, oh yeah, what's the derivative of secant? Secant tangent. I picture the psst in my head. So to find y double prime, we need to find y prime. Okay, derivative of secant is just secant tangent, right? So then y double prime is the derivative of this. So we're going to have to use our product rule. So here's u and here's v. So remember, it's u v prime plus v u prime. That's our rule, right? U v prime plus v u prime. So here we go. U secant of x times v prime. Well, that's secant squared of x. That's the derivative of tangent, right? Secant, secant. Plus v, tangent of x, u prime. Well, the derivative of secant is secant tangent. Okay, so now let's rearrange here, and we'll put everything where it needs to go. And when we clean it up, here's my second derivative. We get secant cubed plus tangent of x, secant squared of x. So here's how we can use these trig functions to find some answers. And this is a good overview of how we can apply, these trig rules and find these derivatives. So this is a good place to kind of stop and take a break. There'll be another video where we kind of explore applying these trig functions just a little bit more, maybe using our calculator. But this is a good rundown of the algebra and applying these derivatives, especially using the product rule and the quotient rule, because that's most often what's going to trip you up, is not recognizing I need to apply another rule here to do my product rule or my quotient rule. So I hope this has been helpful. Please, as always, make sure that you reach out with questions along the way. And remember, mastery is not expected the first time around. So if you are still struggling, remember, it's only through practice that you're going to get better at this. And I'm here for you. And, I've got 15 years of education experience at this point under my belt. And I can honestly tell you that practice is going to be the way that you get better. And you should never back down from a challenge, because I know that each of you has the ability to do this stuff if you practice and you keep at it. So, as always, I know that you guys can do this. Keep at it. You've got this.